In this lecture, we will derive the equation for power flow through a transmission line in the form of generalized ABCD parameters. Let us see how. We can write Vs as simply AVR plus BIR, where Vs, VR, IR are in phasor form and ABCD are complex quantities. This I have written from this matrix only. Vs Is is equal to ABCD into VR IR. Similarly, Is is simply CVR plus DIR. Now, from this equation 1, I can write IR is simply equal to Vs minus AVR over B. And if I try to somehow eliminate IR from this, what I will get, Is is equal to CVR plus D by B Vs minus AVR equals to, let us say, I multiply by B on both sides, BCVR plus DVS minus ADVR, or if I take VR common, this will be give me AD minus BC, I have taken minus sign out, plus DVS. Now we know for transmission line AD minus BC is equal to 1. So simply Is can be written as minus VR by B plus D by B Vs. Let us say this is equation, let us say this is 2 and this equation is 3 and this equation is 4. This equation number 4 and 3 will be very useful in the derivation of the complex power at both the sending end and the receiving end. Let us first derive the complex power at the receiving end. Now, complex power at the receiving end is simply equals to the real power plus J receiving and reactive power equals to the receiving end voltage into the receiving end currents conjugate. Now, we already know that for a complex number, let us say Zt is equal to Za plus Zb, its conjugate will simply be the sum of these two conjugates. And for the numbers in polar form, the conjugate can simply be written by just changing the sign of the angle. So, if I want to write the conjugate of this, I will have to simply change the sign of the angular part. Now, before proceeding further, I will write some of the symbols which we are going to use. First, I will take reference phasor as the receiving end voltage, and the sending end voltage will be simply Vs angle delta. And this ABCD are complex parameters with value A angle alpha, B equal to B angle beta, C equals to C angle zeta, and D is usually equal to A for transmission line, that is for any symmetrical two-port network, symmetrical passive two-port network, it is true. So I will simply write it as A angle alpha. Now I will put all these values in our equation number 3 and 4, and let us say this is equation number 5 to get the complex polar form of the complex power. So I will write SR is equal to simply PR plus JQR is equals to, let us say, multiply this IR conjugate by VR in equation 4. So it will simply be VR angle 0 multiplied by VS angle delta minus A angle alpha and VR angle 0, and this is B angle beta in its whole conjugate. So what I can write, I can easily write this as VR angle 0 degree VS minus delta minus A minus alpha VR, and this is simply B minus beta. Okay. Now in the next slide I will further manipulate this equation to further simplify it. Let us see how. Here now I have again written the equation which we have derived earlier, and also equation number 3 and 4 because these two equations are very crucial. So further simplifying this, what I will get? I will get SR is simply taking VR inside, and when this will go in the numerator it will become plus beta. So what I will get? VS VR angle beta minus delta over B minus A over B VR square angle beta minus alpha. So this full equation, let us say it is equation number A. Now I will further simplify it into the real part and the imaginary part, writing SR as PR plus JQR, and I already know that Z angle theta, any complex number, can be written as Z cos theta plus J Z sin theta. So I will use this identity here. What I will get? I will get VS VR over B cos of beta minus delta plus J sin beta minus delta minus A by B VR square cos of beta minus alpha plus J sin of beta minus alpha. Now taking the real terms and the imaginary terms together, what I can write? PR is simply VS VR over B cos of beta minus delta minus A VR square over B cos of beta minus alpha. Similarly, QR can be written as VS VR over B sin of beta minus delta minus A VR square over B sin of beta minus alpha. Now let us call it as equation B and this as equation C. Now for a short transmission line, the value of A is usually equal to 1 angle 0 and it is equal to D, and B is simply the impedance of the line, which is usually reactive in nature, and I can usually write it as X angle 90 degree. That is, theta is usually 90 degree for practical transmission line. So practically A and D are approximately equal to 1 and B is normally equal to the reactance of the line if I neglect various approximations. So, and this equation in this form will be true for short lines, because for short line already we know that A and D are equal to 1 and B is simply the impedance of the line. Now using these approximations in equation B and equation C, I can further simplify them, which we'll see in the next slide. Now let us further simplify the equation for the real power and the reactive power at the receiving end using our approximations, in which I have written A is equal to D is equal to simply 1 angle 0 and B is simply X angle 90 degree. Okay. So what I will get, PR is simply VS VR over X cos of beta minus delta. This is 90 minus delta minus VR square over X cos of beta minus alpha. So what I will get? I will simply get VS VR over X cos 90 minus delta is simply sin delta and cos 90 is simply 0. So you see this equation is very important equation, and we will encounter this equation in various chapters, because this is true for any network in which it is just connected by a reactance X and we want to find the value of the receiving end real power when we are given VS, IS, VR, IR. So it is simply the real power at the receiving end is simply the product of the magnitude of voltage at both ends divided by the reactance in between those terminals and the angular difference between the sending end voltage and the receiving end voltage. So you see this equation is very important and very easy to remember also. We will also encounter the similar equation in electrical machine chapter when we will try to study the power of the synchronous machines. So similarly I can find QR equals to VS VR, B is simply X, sine of beta is 90 minus delta minus VR square by X sine of 90 minus 0. So what I will get, QR is simply VR over X VS cos delta minus VR, because sin 90 is equal to 1. Now usually the value of delta is very small, so cos delta will be approximately equal to 1. So what I will get here, that the receiving and reactive power is nothing but VR over X into VS minus VR. So what it is? It is nothing but the difference between the magnitudes of the sending end voltage and the receiving end voltage, or I can simply write it as the magnitude of the change in voltage across the length of the line into VR over X. So you see that the receiving and reactive power is proportional to the voltage drop across the length of the line if the receiving end voltage is termed as constant or taken as constant. So you see that to avoid a very large drop across the length of the line, we somehow try to minimize this requirement. If I somehow minimize the reactive power demand on the line, then the voltage drop across the length of the line will be reduced. That is, the voltage profile, let us say, is like, you see, like this. That is, this is Vs and this is Vr and this is delta V. Now if I want to reduce this gap, that is, I want to, let us say, try to get this kind of voltage profile. That is, I am trying to reduce this delta V. What I should do, I should reduce the demand of reactive power on the line. So you see, in reactive power compensation for control of the voltage at the receiving end, what we do, we try to minimize the demand on the line of the reactive power which is required. We usually try to supply this reactive power locally at the load end using shunt capacitors. Similarly, if delta V is negative, that is, voltage is increasing, so what we will do, we will put shunt inductors on the load end of the line so that the voltage profile is again smooth or flat. So you see, from these two equations, this is equation 1 and let us say this is equation 2. From these two equations, I can easily find the value of the receiving end real power and the receiving end reactive power only if I know the value of the magnitudes of various voltages and the reactance of the line and the angular difference between these two voltages. Now, it is very easy to determine the value of the complex power at the sending end. I will just simply write the equation on the next slide, and it is recommended that the viewer derives this equation by themselves. So let me see and write the equation of the sending end complex power in the next slide. Now in this slide I have written the equation of the sending end complex power. It is very easy to derive this equation and it can be derived in the similar way which I have used for the derivation of the receiving end complex power. What I will do, I will simply write Is conjugate from equation 3 and I will just simply multiply this by Vs to get Is, this Ss, that is the complex sending end power. So in this way I will derive this equation. So in this lecture we have derived the equations for the power flow over the transmission line. These equations are very general in nature. We have used some approximation which are usually correct in practical lines. So the results which we will get from using these equations will be quite accurate for the use in practical domain. And I hope these equations will be very helpful to you, and these are very simple to remember also. So if you find this lecture is helpful to you, then it is requested that you please share and subscribe our YouTube channel. Thank you.